our today's investigation about heat recovery process, which was introduced recently in all the countries. And we are glad that we also have one example in Lithuania, which is successfully recovering energy from CO2 plant. So that's very nice experience. And I see some colleagues in the meeting had also been visiting us and discovered a nice CO2 application, which was, behaving nicely. So we had got some experiences what to do. Okay, so we will speak about heat recovery unit. That is something what was invented, assembled by Danfoss. It was engineered, and it is dedicated to accommodate extra energy, which is sometimes wasted. So in order to meet our growing need for development of infrastructure, food supply, and energy efficiency and climate-friendly solutions, we will speak about the device, which is called in English HRU, or heat recovery unit. All our conversation will be about 1 hour long, but just very few slides can represent complete topic of what we will speak about. So the unit is prefabricated for CO2 powered cooling applications, especially. It can accommodate, or it can be used in different purposes, and heating, just heating of a building, just preparing hot water. It can potentially actually also sell or be used for selling of surplus energy to district heating utility. We are speaking with Vilnius district heating utility. What can be done? How can we connect supermarkets to provide energy to heating grid? There are issues, of course, how to stabilize temperatures, how to sell quality product, but these are issues which are already in business in Nordic countries, especially in Denmark. So what do we have? We have factory assembled unit. It is of two, we may say so, sizes with 1 or 2 tanks. I will take some. It might be with 1, 2 tanks, either with 1 tank for small sizes. It's very compact, actually. It's about 2 meters tall, 2.7 meters wide, and 1.2 meter deep. Mainly depth belongs or depends on heat exchangers, which are protruding here. So all our goods are made in the factory. Sometimes we are discussing what is factory-made product and what is made on site. So factory-made product mostly would be compact. It's saving space. It's engineered so that it is assembled in the most compact way, and it is also assembled and produced according to standards which manufacturer is following, like ISO or automotive industry set guidelines, and of course we are following pressure equipment directives. So first scenario, no heat recovery at all. Supermarket might chill sausages, milk, and etc., and throw out heat just somewhere on the roof. That's not energy efficient solution. Yep, we're not saving, we're not environmentally friendly, and a supermarket is buying energy from utilities. Another scenario might be very different, and it sometimes depend on the installer or designer solution. So sometimes it's very complicated, needs a lots and a lots of solutions, free programmable controllers to process all the plan or desire of creator. So plumbers are challenged with how to assemble, how to fix, and how to start. So I was speaking to some people, and I discovered that yes, probably you also had that idea that free programmable controllers are not so friendly to the not commissioning, but for the maintaining companies who are maintaining the plant. So each time they're coming to new application, they have to learn what they have to do. And these applications sometimes do not take into the account all the processes. They have actually to combine heat and cool or cooling. Here we come with Danfoss heat recovery solution. It's standardized or standard solution. It's easy to install and commission because of known controller. It's completely insulated, so no heat losses. Buffer tanks are helping to accommodate some energy when it's not needed, so you can load them. The ECL controller, which we're using, is very friendly as for remote diagnostics and remote monitoring. Yes, and our system is also stable and efficient with our solution. Where can we apply that product? In different cooling applications, in different stores, in different places. So I would say here that even I see a potential to utilize this unit together with solar panels, which are heating water, because I had seen so many examples where buffer tanks are charged up to 45 degrees Celsius. And as this temperature is too low for domestic hot water, district heating utilities energy is used. And building, which is some 4,000 or 5,000 square meters big, would potentially be able to utilize this energy in the heating system during April, for example. But it is not capable to utilize, and it is just having a lot of warm and not hot water in the buffer tanks. Key considerations. What is needed? We need a competence to understand completely heating and cooling system to have a positive result. And this slide would probably be the main slide of this presentation, so you can remember it and you can revert to it many times later on. It would explain how do we succeed in good and large energy savings. Here we have pH diagram where we can see how the cooling system is working. I would stress to the point where normally compressor is pressing CO2 in our example to, let's presume, minimal pressure where the system might function where oil is distributed in the compressor just to lubricate. So we may say so that the cooling plant actually can work on something like 40 bars and 65 degrees. How do we relate that chart with our heat recovery? If our heating system or HVAC system is returning temperature to the plant with a value of, for example, 40 degrees, what do we see here? We see here that actually we have a potential of so large potential for the heat reclaim. So as we can see, there is not much we can reclaim. And therefore, if your heating system would be designed for even lower temperatures, for example, 25 degrees, now you see that potential for the heat recovery had increased, not so much. Therefore, we are saying that the plant should be optimized for heat recovery, and compressors might add extra work, so heat pump is just pushed heavier, and we can go to the larger temperatures like 90 or 100 something. Yes, that will lead to higher pressure. And here now we can see that if our plant is designed to deliver 25 degrees back to heat recovery unit, our heat reclaim potential is increasing dramatically. So therefore, we started discussions with our supermarket chains, with people responsible, with designers, and also it goes hand in hand with district heating utilities, imagination about low temperature district heating utilities, that systems, air handling units or something else should be designed for low temperatures. Instead of using 80 supply, 60 return, we are speaking about 60 supply, 30 return. So we are speaking about larger delta T and smaller or lower temperatures. That would bring a higher heat reclaim, because I had so many times that customer or supermarket is saying that, okay, how much heat I will regain or reclaim or I will get back from the device you are showing. So therefore, we are speaking that not only device should be installed somewhere among concrete and iron, the system should be designed to be capable to get the most effective result. How does it land with, somebody would ask, COP or coefficient of positive performance, operation performance? Here you can see that if we are having system with power of 100 kilowatts, and if we are pumping more pressure, here the green one, that's consumption of electricity. Here we can see about our heating COP. It's increasing. So we may say so that probably we might reach the best performance somewhere around 75 bars and etc. Here, cooling engineers would probably discover what is happening in the cooling system when fans off and gas cooler bypass is turned to relevant position. So you can see that actually cooling capacity is staying. We are just increasing COP, so we are gaining extra. So there is no worry for people about that we are pressing harder and that we are turning compressor harder. We're just making energy from cooling machine. Therefore, we are saying that systems should be combined together for the best result. Some who would like to manipulate with figures and to calculate possibilities of heat reclaim might discover Pack Calculation Pro on the internet and might exercise what will happen. Here is an example of small plant with 44 almost kilowatts of cooling capacity or demand, place Kaunas, Lithuania. And we have three scenarios. When return temperature is 45, 35, 25. We are spending 50,000 kilowatts for fans, pumps, compressors in all scenarios. And as regards of heat reclaim, with a high temperature, we might reclaim so much, 39,000. With 35, it's 52. And with 25 degrees, we can get 105,000 kilowatt energy back. So again, when speaking, HVAC and cooling guys, talk to customers, talk to supermarket chains. Don't be afraid of twice larger coil in your air handling unit. Yes, you will increase space in the air handling unit. On the other hand, when speaking delta T 30 degrees for the cooling, your pipes and all the rest of the things like valves, fittings, whatever, labor cost will decrease because of flow will be lower. Other benefit, of course, might be, as I spoke, that energy could be sold back to district energy. So maybe some companies would be interested in how to buy energy from supermarkets. Main features. Yeah, probably we may say so. That key feature one, that we are selling standard solution, ready to install. It's already made. Just put it in the place, start it up. Short return on investment. Helps to save money on the longer term. What is also, I would say, important, we are taking quite less space compared to the solutions built on site. And of course, serial automated production leads to higher quality and less mistakes. Yep. We say that it's solution with low total cost of ownership. Among the rest, I would underline that we are saving lifetime, or not saving lifetime, but increasing lifetime of a CO2 heat exchanger, because standard solutions quite often are leading to fluctuation of the temperatures, up, down, and if you would like to bend something and try to break something, you would eventually break it. That happens with CO2 exchanger. If it's getting high temperature, high pressure on one side, and suddenly cold water on the another side, so it is stressed all the time. It's working like harmony or something. No, that musical device, I don't know how to call it, but so it's every time stressed. And we know the cases from the market when CO2 was leaking to heating installation, and then suddenly somebody noticed that his application is like some soft drink with a gas with the bubbles. So that's not the best solution for that. user to have a heat exchanger worth of 3,000 euros broken. What's worth to mention that consumption and generation should not happen simultaneously or synchronically. We can prioritize usage of heat recovered energy from cooling unit before supplying from a heat source. And so on and so on. What is worth to mention, it is connectivity of heat recovery unit to the system. We discovered that some of the supermarkets are living, should I say, or they are having scenario when someone is responsible for the heating and someone is responsible for technology, means cooling, and they might have different opinion about connectivity. So that solution should be discussed, and it would be great if heating guys and cooling guys would combine the systems together for the better, proper result. When asking how much it gives me, there are a few scenarios from no heat recovery to heat recovery unit. One of them is including sales to the grid, to district heating utility. Another one is without sale. So we may say that without selling energy back to district heating utility, in average, based on experience from Denmark, heat recovery unit pays back by 2 years. What should be also highlighted, yep. Final energy consumption for the supermarket of 1,000 square meters is reduced by 500 kilowatt hours per square meter per year. That I would say great. And of course you can see how many money you can get back, and that's in Danish crowns. Positive example from Denmark. They say that they sold 90 megawatt hours to district heating utility and they bought 15 megawatt hours. Recovery from supermarket in Lithuania. It's about, we see here about 1 year, we recalculated energy to euros, and we may say so that already 1 year consumed so much money as much the heat recovery unit might be sold for. Yes, that's a large application. Mandatory preconditions. CO2 site should be insulated, otherwise you're wasting a lot of energy because of high temperature difference. System should be set for the heat recovery. There should be a three-way motorized control valve to bypass heat exchanger. There should be a link or connection of power inquiry from heat recovery unit to CO2 plant. And of course, heating and ventilation system must be configured so that they can accommodate energy. Compensators should be fitted between CO2 heat exchanger and the fixed plumbing pipe, because the cooling rack is vibrating because of work of compressors. So the pipe, which is welded or soldered to the heat exchanger, will be stressed every time. Of course, it would be nice to eliminate vibrations. Safety valve should be on the water side, just to open on sudden temperature increases. And of course, operation of cooling plant should be set correctly to avoid excessive starting and stopping, and like we have an example of poor compressor maintenance. As regards of insulation, we have a brown line which is speaking about desire, and we see here on the blue line the real gain. What we're speaking about here, about poor insulation, and that customer lost some 7,000 euros on application because of, system was not optimized, not to insulate it. Typical application. Few words about typical application which is used nowadays without heat recovery. There would be probably 2 blocks of mechanics inside. They would contain three-way valve, which is bypassing hot gas either to the recovery, either to the gas cooler. Typically, here we would have a tank with a coil or something inside, and that coil would be used to heat domestic hot water. That application typically is recovering about 10% of potential only. The next copy-paste block would be following first block. It would be also made of a three-way valve and of a heat exchanger, which is normally used in the supermarkets to heat up or preheat air, which is used for the ventilation. The solution with the 2 heat exchangers actually costs more because you have to use 2 heat exchangers, 2 three-way valves, and that might lead to, for example, 3,500 euros extra. So if someone will tell that my heat recovery solution, which I'm using now, is worth of 5,000 euros, he will not include idea that customer should buy the cooling rack, which is worth also plus 3,500 euros up. So actually, instead of telling my solution is 5,000, he should tell my solution is 8,500 euros. Another topic, when we are speaking about secondary heat exchanger, which is not drawn here, you have to build double heating system for the air handling unit. I mean, 1 heat exchanger from the cooling rack will accommodate it, plus heat exchanger, plus hundreds probably of meters of pipes to the air handling unit. Air handling unit will be larger. It will have 2 heat exchangers, because one will be from heat recovery, another one will be from district heating utility. So customer is buying 2 systems. And when we compared one of the systems for 300 kilowatts, we discovered that the pipes will be about DN80 or 80 millimeters in diameter. The complete system of pipes installation might be worth of about 4,000 euros, just like that. So customer is paying for the piping just 4,000 euros extra. Glycol, which should be poured in, would cost another 1,500 euros. So you see, it's not so easy to compare the systems. When customers are comparing separately, not combining complete solution in one package, then they're mixing, actually result they're missing the figures where they should look at. In our case, in our scenario, we're using only one heat exchanger, which is taking as much of the heat as possible, and it looks like that. Our heat recovery unit is connected to heat exchanger. We are pumping energy to tanks. We are raising energy up, and we are delivering it to building. In the next slide, in the coming slides, it will be more easier to see how is it working. With this slide, I would like to show you the ECL 310 controller, which we're using now, and which is capable to run a specific program of the heat recovery. We are utilizing combined solution of master and slave. So slaves in the building might ask from the master to deliver temperature they want. And it looks like that. We are recovering energy to the tanks. We are sending energy to freeway valve, and we are sending energy to the building. When we need something here, for example, we need domestic hot water, and we are missing, not missing, but the temperature in the tanks is not high enough, despite we are asking from energy from heat with a signal from heat recovery to the cooling rack that please chill down sausages, not chill down the sausages, switch on your heat pump more, make us more energy. If that is not working, then we are calling for the heat from the district heating utility or from the boiler plant, and we are raising temperature to the building. So we are capable to heat up domestic hot water, to process anti-legionella feature, and etc. When we are over with the domestic hot water, when it's not needed, we are reverting back to heating, to the air handling unit. And there are also possible scenarios when we can close heating and ventilation during hot water preparation. If one of your circuits is air handling unit is supplying air handling unit, yep, then probably we might face somewhere here a heat exchanger, which is probably separating water from the glycol. So generally speaking, all that part is filled with ordinary water, not glycol. So that's how does it work. And here you can see additionally 4 sensors. These 2 guys on the return are used to keep heat exchanger from the stress. So we are not pumping fast because we are utilizing PWM modulation control algorithm, and we are not running pump with a start-stop algorithm. So we are gradually increasing, gradually decreasing speed of the pump, and we are keeping balance here. And of course, we are monitoring temperatures on the supply side. So that's how does it work. To repeat, quite simple. Charging tanks, sending to the building. If building is requiring extra efforts, he's telling us change something, then we can change by inviting district heating utility. Either we can ask more energy from the cooling rack. Quite simple. Okay, here I have a balancing valve, which we are using just to prevent of too large flow, because it's quite difficult for us to align pump and heat exchanger in the plants. Portfolio. Heat recovery units are made in Gdansk, Poland, our substation production site. They are mainly made of two sizes, or two models: small stores, larger stores, small stores, one tank, larger stores, two tanks. We have few types, A1, A3, etc. They're different, I will show you later on. Heating demands up to 540 kilowatts. If you would browse our data sheets, you would discover these figures. Be aware that these kilowatts were calculated with estimation that delta T on plant or building site will be 30, not 10 or 20. And max recovery of 400 kilowatts from CO2. Here we go, few examples. The difference is heat exchanger, no heat exchanger, just one tank. So application A6, A7. Two tank solution, 1, 2, 3, 4 versions. What I would like to underline for designers is that we are telling that our maximum primary temperature is 90 degrees. I was discussing with the plant, and we agreed that they will produce a special unit on our inquiry with larger temperature, 120 degrees. The difference is you can see these ball valves, which are made in the row 2, 2, 2. So we have 6 ball valves. Actually, we need 2 of these ball valves to be changed to welding ball valves, or ball valves made from steel, which could be welded to the district heating utility primary site. So that is in general changing status of station to 120 degrees. Other topic, flows. Maximum flow primary and secondary 15 cubic meters per hour with a speed of 1.2 meters per second. At the moment, sometimes we're facing inquiry for the bigger, larger station. We are discussing with the manufacturer about that. It's complicated because demand of the market is rather low, and we are analyzing different possibilities. Yep. These were things I wanted to highlight. Application with two tank solution and with possibility of sale of energy. So we have extra appendix here. So when we are over with the charging of the tanks, so tanks are charged, building says I don't want energy, so we can start gradually pump P4. Also, we should install here additional pump with a frequency converter, and we are gradually starting force pumps to increase pressure. And when we are overcoming pressure in the supply line somewhere here, we're connecting these pipes, and we can gradually start selling or delivering energy to district heating utility. As long as we have energy here, of course. Other applications 2, 3, 4. The main applications we are focusing now in Lithuania are these two. One with the heat exchanger when we are speaking about district heating utility, and one is without it when we're speaking about boiler house, where energy is coming from the boiler house. Yep, insight about value proposition. When heat recovery unit will start operating, yes, you will be able to recover energy with highest performance. The complete solution will be delivered. And of course, the system will be of high quality and it will be very friendly for the service. Our product is completely produced, designed, so there will be minimal demand for maintenance. It's compact. You will save space. It's fully insulated, so energy losses will be smallest possible. It's modular build. Actually, you can split heat recovery unit to, for example, 3 pieces, and you can take it to the building almost through any door which is allowing 1 meter or something to be pushed through. It's easy to design. Pipes of a heat recovery unit are always in the same order. Supply to the building and recovery pipes. So that's quite simple. You can just design pipes which should come to the certain place, and you can wait until heat recovery unit will be delivered into for the installation. So you can work simultaneously. You shouldn't wait for something. Yes, and it's designed to set the high standards on energy efficiency. We're using high efficiency pumps from leading pump suppliers with PWM signal, as I said. We're using specific key for the application. We're using ECL Portal Cloud for the monitoring. An ECL 310 controller can be connected to other Danfoss cooling devices. Heat exchangers are produced with a microplate technology. There is a very nice seminar or webinar arranged by Mark from Danfoss heat exchanger business unit. You can check it out. It's very useful to refresh your knowledge about heat exchangers or plate heat exchangers. Special buffer tanks. Our buffer tanks are specially designed with specific inserts inside, which are enabling water to be loaded and charged without any short circuits in the water flow. So it's very nicely charging. And then for CCL Portal, of course, it's 24/7 easy access of the application. Components we're using, yes, they were just mentioned. Best pumps, ECL, our programs and SCADA units, and models of the heat exchangers, which are made of, as you can see, dimple or microplate pattern, which is allowing heat exchanger to be more effective compared to the ordinary fishbone pattern. Our station is completely insulated. Valves have a specific covers, pipes are insulated, so even joints are insulated or delivered. Insulation is delivered for the joints to be insulated when station is connected to the plant. We have electrical drawing chart or electrical chart. Station is packed so that it is not how should I shaking inside. As you remember, I said that it's easy to design. Pipes are always in the same order. Here we have a plant with 4 pipe groups. Normally, we're not using fourth, and it's not installed if we are not selling energy. So there are 3 pipe groups we're normally using. Scope of delivery is we are delivering unit and few sensors are delivered as loose for local installation. And here we have some information about how do we monitor. We might use PC or Mac or smartphone, and we can check our plant. How does it work? What's cooking around? How much energy we recovered just in the cloud, in the ECL portal. And of course, we can connect everything to Danfoss cooling management system. Yes, we have a complete portfolio of handling of food and safety, different monitoring devices, different managers or devices on site. And from the complete range, I was speaking today just about this very small guy, about heat recovery unit, which is using ECL control and which can be connected to our cloud solution. Here is a slide about possibility of sensor data reading and transmitting everything to AK system or cooling control system. So that was it. I presented for you a heat recovery unit made by Danfoss. Just to wrap up, please remember one very chart I showed you, that the heating system should be designed to be capable to accommodate as much as possible of energy. So the result of the customer will be highest, largest, and I would say there is no point of hearing of a system with low temperatures. Another thing about price, you should compare complete package of 2 units of cooling rack, of heat recovery rack all together and installation of a building. Then you will discover complete package. So now I'm ready to listen and read your questions. Please raise your hand or type your question here and I will answer them. Please. Yep. I don't see risen hands. I don't see questions. Any of them? You have a microphone.
Walters would like to ask.
Yeah, please do unmute and mute your microphone. It's on the left hand. I can.
Yes, hello.
Yes, hello.
Can you hear me?
Yes.
Yeah, I wanted to ask about what are the principles or rules when you choose the tank size? Because, for example, in summer, you will have the biggest heating power accessible from the cooling plant, but in the winter, the lowest. So, yeah, I'm interested in how do you choose the tank size based on what rules or principles?
They were based on the practical discoveries from heating and cooling engineers from Danfoss. And if you would browse internet for heat recovery unit datasheet, you will discover datasheet which would include a table with a heating capacity chart and with cooling recovery data. And you would discover that mainly the scenario is very simple. As Danes did, shops smaller than 1,500 meters, they are offering solutions with 1 tank, and shops with a larger capacity, they are offering 2 tanks. So actually, these figures or these calculations are in the hands of my employer, of my colleagues in Denmark. They decided which model should be of what size. And that was partly coming from their own experience. So we don't provide any table which would tell you how many liters should be if your capacity for something is so large and capacity for different is so large. I partly answered and partly didn't to your question. Yep.
Okay, thank you.
Yep. Yeah. Any other? Any other, please do.
If I can ask one more thing.
Yeah. Sure.
What is the approximate volume of the one tank, for example?
I skipped that in presentation. 500 liters. One tank, 500 liters. Two tanks for 1 ton about. Yep. It's not a buffer of 500 cubic meters or something. Yes, it's actually used for temporary, I would say, compensation of going ups and downs. Because normally we are putting energy to the to the building, and in summertime when we need just domestic hot water, another alternative was discovered that tanks can sell energy. So issue at the moment is, at least in Lithuania, the district heating utilities have their own scenario when you can sell energy. You have to go a longer journey, you have to be an independent energy supply, and etc. That's quite long stuff. I do not know how is it in Latvia, Estonia. How do you do it then? Maybe it's possible. Maybe there are some obstacles also. Okay, any more? Any dilemmas, any hard, deep questions? How did you like, for example, higher delta T and lower temperatures, as from the designer point of view? Anybody can just share his opinion. High delta T, low temperature, is it evil or is it something good? Just raise your hand, somebody, and unmute microphone. Nope. I know just Aller, but I don't know, he's not speaking. Okay, okay, see, hello, yes, and I'm challenged every time with that sophisticated tool. Hello. Actually, I do not. I can't read that question. I will ask in written. Yeah. Okay. Okay. Fine. Agris wanted something. You can now ask in, I don't know, in well, in language. Okay. Then I don't know, maybe Agris wanted to ask something, but I don't see his message. Yeah, okay, you will write in mail, fine with me. Okay, so colleagues, no more questions, and I would thank you for the webinar, thank you for coming, and as they say, have a nice day. We will have a free day tomorrow, but yeah, please do write to our colleagues in Danfoss, and we will help you with these questions. Thank you, and then we are over. Okay. Yep. Bye.